Hello everyone. Welcome back to my course Aerospace Engineering, Complete Drone Guide. In this video, we will talk about drone sensors and GPS. Also, I will be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. Drones have transformed the way we explore, work, and interact with the world around us. From supporting military operations to streamlining logistics and delivery services, these flying machines now perform tasks that were once difficult or even impossible. However, behind every smooth flight and precise maneuver lies a complex network of sensors that quietly ensure everything works as expected. These sensors allow drones to navigate safely, maintain balance in the air, detect obstacles, and respond intelligently to changes in their environment. Without them, modern drones would lack the stability, accuracy, and reliability required for real-world applications. In this section, we explore the different types of UAV sensors, how they contribute to safe flight, and the technologies shaping the future of drone navigation and stability. By the end, you will understand how these systems make drones smarter and capable of handling a wide range of missions. Types of drone sensors. Drones rely on multiple sensors to understand their surroundings, maintain control, and execute tasks with precision. These sensors can be grouped based on their function and role in the drone system. Navigation sensors. Navigation sensors act as the drone's positioning and orientation system. These include GPS modules and orientation sensors that help determine the drone's exact location, speed, and direction. They are essential for automated flight paths, route planning, and safe operation in complex environments. These sensors are widely used in delivery drones, agricultural drones, and military UAVs, where precision navigation is critical. Flight stability sensors. Flight stability sensors include gyroscopes, accelerometers, and barometers. These components continuously monitor the drone's movement, tilt, and altitude. Their primary role is to maintain balance and ensure smooth flight, even in challenging weather conditions such as wind or turbulence. Without these sensors, drones would struggle to remain stable and could easily drift off course. They are especially important in photography, inspection, and crop monitoring drones where steady hovering is required. Obstacle detection sensors. Obstacle detection sensors allow drones to identify and avoid objects in their path. Technologies such as ultrasonic sensors, infrared sensors, LiDAR, and vision-based cameras enable drones to see their surroundings. These sensors operate in real time, helping prevent collisions and ensuring safe navigation, especially in complex environments. Ultrasonic sensors use sound waves to detect nearby objects, while infrared sensors identify obstacles based on heat or proximity. Vision-based cameras capture visual data that is processed by intelligent algorithms to recognize objects. LiDAR adds another layer of precision by creating detailed spatial maps. By integrating multiple sensing technologies, drones can react quickly to changes in their environment and navigate safely even in confined or cluttered spaces. They are commonly used in logistics and military drones. LiDAR technology in drones. LiDAR, which stands for light detection and ranging, is an advanced sensing technology that allows drones to create detailed three-dimensional representations of their surroundings. It works by emitting laser pulses toward objects and measuring the time it takes for the light to return. This information is then used to generate highly accurate 3D maps. LiDAR-equipped drones are especially valuable in applications where precision is critical. They are used in military reconnaissance for terrain mapping, in logistics for navigating urban environments, in maritime operations for coastal scanning, and in agriculture for analyzing field conditions. Unlike GPS, LiDAR can provide reliable data even in environments with poor satellite coverage, making it a key technology in advanced drone operations. Environmental sensors. Environmental sensors measure external conditions such as temperature, humidity, wind speed, and air pressure. This data helps drones adapt to changing weather conditions and optimize flight performance. These sensors are particularly useful in agriculture, environmental monitoring, and disaster response operations where conditions can change rapidly. Payload sensors. Payload sensors are specialized tools carried by drones depending on their mission. These include cameras, thermal imaging devices, and LiDAR scanners. They collect valuable data for applications such as surveillance, mapping, inspection, and reconnaissance. These sensors are critical in industries like agriculture, logistics, and defense. Each type of sensor contributes to the drone's overall intelligence, enabling it to operate safely, efficiently, and autonomously. Advancement of sensor technology in drones. With the rapid advancement in drone technology, a wide range of sensors have been integrated into modern drones to significantly improve their capabilities. These sensors enhance the sensitivity of drones, allowing them to collect critical project data with greater accuracy and reliability. At the same time, they improve the drone's ability to maneuver through challenging and complex terrain, which would otherwise be difficult to navigate. With the help of these sensors, drones are able to maintain their position in the air, determine their speed, and avoid obstacles effectively. These capabilities are essential for both basic flight operations and advanced applications across industries. In this section, we will review several important sensor technologies used in modern unmanned aerial vehicles, UAVs, providing a deeper understanding of how each one contributes to drone functionality. Core sensors installed in a drone. When discussing drone sensors, several core components are commonly included. These include the inertial measurement unit, air pressure sensors, magnetic compass, GNSS systems, and optical or acoustic sensors. Inertial measurement unit, IMU. The inertial measurement unit is one of the most critical components in a drone. It consists of sensors that measure acceleration and angular motion or rotational movement across 3 axes. This data is processed by the flight controller and used to adjust motor speeds for stable flight. Unlike fixed-wing aircraft, multicopters cannot operate without an inertial measurement unit. This data is extremely important because it can be used to calculate the drone's position and velocity during flight. IMUs are a fundamental component of inertial navigation systems. These systems are widely used not only in drones but also in aircraft, other unmanned systems, missiles, and even satellites. Their importance lies in their ability to provide continuous motion data without relying on external references. The performance of an IMU has a direct impact on drone flight quality. An IMU with strong vibration resistance and high accuracy will significantly enhance the drone's flight performance, making it more stable and responsive during operation. An IMU typically consists of several internal sensors working together. These include accelerometers, which measure angular velocity, gyroscopes, which measure angular rate, and optionally magnetometers, which measure the magnetic field surrounding the system. The combination of these sensors allows the IMU to provide a complete picture of motion and orientation. Accelerometer. Accelerometers play a critical role in determining the position and orientation of a drone during flight. They measure the acceleration force acting on the drone across three axes, known as the X, Y, and Z axis. This allows the system to understand how the drone is moving in three-dimensional space. In addition to measuring motion, accelerometers also help determine the tilt angle of the drone when it is stationary. For example, if a drone is resting in a perfectly horizontal position, the X and Y axis will produce a reading of 0g, while the Z axis will produce a reading of 1g. This value represents the gravitational force experienced by all objects on Earth. If the drone rotates by 90 degrees along the X-axis, the readings will change accordingly. In this case, the X and Z axis will show 0g, while the Y axis will show 1g. During any tilt or rotation, the accelerometer outputs values between 0g and 1g across all three axes, depending on the angle and movement. Accelerometers also measure linear acceleration in both horizontal and vertical directions. This data can be used to calculate velocity, movement, and even the rate at which altitude changes. These calculations are essential for maintaining accurate and stable flight. When combined with GPS technology, accelerometers can enhance navigation accuracy. This is similar to how smartphones and fitness devices track movement and routes during activities such as running or traveling. By combining these data sources, the system reduces errors and improves overall accuracy. Accelerometers also contribute to obstacle detection. By monitoring changes in acceleration, the system can detect when the drone is approaching an object and adjust its path accordingly. This adds an additional layer of safety during flight. Another important function of accelerometers is maintaining stable hovering. For example, if a drone is flying in a straight line and encounters a gust of wind, the accelerometer detects the sudden change in motion. The drone's control system then responds by adjusting its position to maintain stability. The most commonly used accelerometers in drones are MEMS, micro-electromechanical system accelerometers. These are small, lightweight, and cost-effective, making them ideal for drone applications. MEMS accelerometers are highly sensitive and can detect changes as small as 0.001g while measuring acceleration across all three axes. Gyroscope. Gyroscopes are essential tools for measuring and maintaining a drone's orientation. They are particularly important in applications such as aerial photography, where the drone must remain stable and level to capture high-quality images. Gyroscopes are often used together with accelerometers. While accelerometers measure linear motion, gyroscopes measure rotational movement. Together, they provide a complete understanding of the drone's position and orientation in three-dimensional space. The use of gyroscope technology plays a key role in maintaining a stable hover. When a drone experiences unwanted drifting or wobbling without any input from the pilot, the gyroscope detects this movement. The data is then sent to the flight controller, which adjusts the motors to counteract the motion and restore stability. A gyroscope measures angular velocity across three axes, allowing it to detect changes in pitch, roll, and yaw. These are the three primary rotational movements of a drone. By continuously monitoring these movements, the gyroscope ensures that the drone responds accurately to control inputs. In addition, gyroscopes ensure that the drone rotates at the exact angles expected by the user. This precision is crucial for maintaining control and achieving smooth, predictable flight behavior. Magnetometer. A magnetometer is a sensor that measures the intensity and direction of a magnetic field. In drones, it provides data about the Earth's magnetic field along the X, Y, and Z axes. This information allows the drone to determine the direction of magnetic north and adjust its course accordingly. This is especially important for navigation and maintaining a consistent flight direction. In addition to direction sensing, magnetometers can detect surrounding magnetic interference and nearby ferromagnetic objects. These may include electricity poles, power lines, vehicles, or even other drones. Detecting these elements helps reduce the risk of accidents and improves overall flight safety. Air pressure sensors or barometers. Air pressure sensors, also known as barometers, measure altitude based on atmospheric pressure. In drones, this data is used to calculate altitude. As a drone moves higher above the Earth's surface, air pressure decreases. By measuring these changes, the drone can determine its altitude, maintain a stable flight level, and respond to sudden environmental changes such as wind gusts. This is especially important for tasks that require consistent height control. Magnetic compass. The magnetic compass helps the drone determine its orientation relative to Earth's magnetic field. It is essential for maintaining direction during flight. However, interference from electromagnetic sources like power lines can disrupt its accuracy and affect flight stability. Acoustic and optical sensors. Acoustic sensors, such as ultrasonic sensors, measure distance using sound waves and are often used during landing. Optical sensors use cameras or infrared systems to detect obstacles and measure movement relative to surfaces. All these sensors work together to simplify flight control and enhance the drone's capabilities. Global Navigation Satellite System. Global Navigation Satellite System allow drones to determine their position on Earth using satellite signals. Modern drones can use multiple satellite systems such as GPS, GLONASS, Galileo, and Beidou. The more satellites available, the more accurate the positioning. GPS sensor. GPS technology has played a critical role in enabling drones to perform autonomous missions. A GPS sensor determines the drone's position and helps guide its movement by comparing its current location with a target position. Based on this comparison, the system sends commands to the motors to adjust direction and movement accordingly. This allows the drone to follow planned routes and reach specific destinations accurately. Drones are equipped with GPS receivers that can receive signals from multiple satellites. The time it takes for signals to travel from the satellites to the drone varies depending on their positions. By analyzing these time differences, the drone calculates its exact location through a process known as triangulation. The accuracy of this positioning depends on two main factors: the strength of the signals received and the number of satellites available. Stronger signals and a higher number of satellites result in more precise location data. Role of navigation sensors in safe flight. Navigation sensors form the foundation of a drone's ability to fly accurately and safely. These systems typically include GPS modules, magnetometers, gyroscopes, and accelerometers. We have already learned that magnetometers help maintain orientation relative to Earth's magnetic field. Gyroscopes and accelerometers monitor motion and tilt, allowing the flight controller to maintain balance, and GPS provides precise location data. By combining these sensors, drones can follow predefined flight paths, hover steadily over targets, and return safely to their starting point, even in unfamiliar or challenging environments. Importance of sensor fusion. No single sensor can provide a complete understanding of the environment. Sensor fusion is the process of combining data from multiple sensors to create a more accurate and reliable picture. For example, GPS data can be combined with inertial measurements, LiDAR data, and camera input to maintain stability and awareness, even when one system is limited. This approach enhances flight performance, improves obstacle detection, and enables advanced autonomous capabilities. Emerging sensor technologies. Drone sensor technology continues to evolve rapidly. New innovations are expanding the capabilities of drones and improving their performance. Hyperspectral sensors can capture detailed data across a wide range of wavelengths, making them useful for advanced analysis. Thermal imaging sensors detect heat signatures, allowing drones to operate in low visibility conditions. Modern LiDAR systems offer faster scanning speeds and higher resolution mapping. AI-powered vision sensors can analyze visual data in real time, enabling smarter decision-making and improved obstacle recognition. These advancements are making drones more intelligent, efficient, and capable across a wide range of industries. Importance of drone sensors in modern applications. The sensors discussed above play a crucial role in the design and development of modern drone systems. As UAV technology continues to advance, more industries are recognizing the value of combining drones with advanced sensor systems. These sensors allow drones to perform a wide variety of tasks with high precision and efficiency. From data collection to navigation and obstacle avoidance, they are essential components that enable drones to function effectively in real-world environments. By understanding how these sensors work, drone pilots and operators can better appreciate the complexity behind drone flight. This knowledge also helps them operate drones more effectively and safely, ensuring optimal performance in different applications. Okay guys, now let's have a little quiz. The quiz consists of 10 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What is the primary function of navigation sensors in a drone? The correct answer is to determine the drone's position, speed, and direction. Question 2. Which sensor is primarily responsible for measuring altitude using atmospheric pressure? The correct answer is barometer. Question 3. What is the main role of a gyroscope in a drone? The correct answer is measuring angular velocity and maintaining orientation. Question 4. How does LiDAR technology help drones? The correct answer is by creating detailed 3D maps using laser pulses. Question 5. What is the purpose of sensor fusion in drones? The correct answer is to combine data from multiple sensors for better accuracy. Question 6. What is the main purpose of an inertial measurement unit IMU in a drone? The correct answer is to measure acceleration and rotation for calculating position and velocity. Question 7. Which type of sensor uses sound waves to measure distance, especially during landing? The correct answer is acoustic sensor. Question 8. What happens to air pressure as a drone increases its altitude? The correct answer is it decreases. Question 9. Which sensor helps the drone determine direction relative to Earth's magnetic field? The correct answer is magnetometer. Question 10. What factor improves the accuracy of a drone's GPS positioning? The correct answer is stronger signals and a higher number of satellites. Unlock the world of aerospace engineering with my other expertly designed courses. In aerospace engineering, Basics of Aerodynamics, you'll explore how air interacts with moving aircraft and how aerodynamic forces influence performance, giving you a strong foundation in the principles that enable efficient lift, stability, and control in modern flight. Then, take your knowledge to new heights with aerospace engineering, aerodynamics, and structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Finally, expand your expertise with aerospace engineering. Rocket Science Basics, where you'll learn about the fundamental principles that govern rocket design, propulsion, and spaceflight, bridging the gap between theoretical physics, engineering structures, and launch systems. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about drone radio transmitter and receiver. See you in the next video. Bye.